Hello everyone. Welcome to lecture 11 of the course on quantum entanglement and non-local games. So we have already looked at the embezzlement game. We have also looked at a quantum input game. Our claim was that this is a game where it is possible to succeed with probability as close to 1 as possible. However, in the limit of probability being 1, we'll actually need infinite dimension of entanglement. And we saw that for embezzlement game indeed it was true, but what remains to be proven is the relationship between the embezzlement game and the quantum input game. So let's see today. So today we are going to look at the equivalence between embezzlement game and the quantum input game. So we are actually going to see two claims. So first claim would be that embezzlement with fidelity greater than equal to 1 minus epsilon, this would imply winning our game with probability 1 minus order root epsilon. Okay, and so we have already seen that this embezzlement with fidelity greater than equal to 1 minus epsilon, this is indeed possible, and we were able to perform it using a dimension which was like order 1 over epsilon. And so this will imply that we can actually win this game with probability 1 minus epsilon, provided we can actually have a dimension of 1 over epsilon square. So let's see that now. So let's prove this claim first. So this claim essentially shows the possibility of winning this game with probability as close to 1 as possible. Okay, because we have already seen that embezzlement game is possible to win with fidelity arbitrarily close to 1, and this would imply that even winning our quantum input game is possible with probability 1 minus order root epsilon. So let's see. So let's look back at that game. So in the game we actually had Alice and Bob. They were given a quantum state as input. This quantum state was of the form ket phi k. So ket phi k was either ket phi 0 or ket phi 1, right? Okay, and Alice was required to produce a bit A, Bob was required to produce a bit B, so these are all single bit, and essentially they win the game if A XOR B equals K. So basically if K is 0, that is if they receive ket phi 0 as input, then they must output equal bits. If K is 1, then they must output unequal bits, opposite bits. And if we recall, our ket phi k was defined as 1 by root 2 ket 0 0 plus minus 1 to the power k times half of ket 1 1 plus ket 2 2, right? And what we can do is that we can consider a representation. Instead of qubits, let's talk about 2 qubits. So qubit, we'll replace it with 2 qubits. So these are qubits shared by Alice and Bob. So I'll write A and B over here. So how I encode qubit in terms of 2 qubits is actually slightly it's slightly different from the usual norm. So how I'll do it is that I'll encode 0 as 0 0, but I know that binary representation of 1 is 0 1, but I'm going to do something different. I'll just encode 1 as 1 0 and I'll encode 2 as 1 1, right? So you might find it strange that that 1 is actually 0 1 and 2 is 1 0, but the reason I'm doing this is that this is just an encoding, and in an encoding we are free to perform any sort of encoding, and this is how it will work. It will just make the analysis more cleaner, but otherwise you could have done a different encoding also in terms of qubits. So here let us try to write down the qubits, the states in terms of these 2 qubit representations. So cat phi 0, which I saw, was 1 by root 2 0 0, but now this 0 0 is actually 0 0 a, because 0 of a is mapped to 0 0 a and 0 0 b, right? And actually what I'm going to do it is that I'll make it slightly different. I'll just make it as 0 0 ab, 0 0 ab. Okay, so these 2 zeros are of a, these 2 zeros are of b. Okay, so we will see a reason why we are writing it this way. Plus 1 by root 2 times, now see here, so here I have 1 1 and 2 2, right? So 1 1 is going to be 1 0 1 0 and 2 2 is going to be 1 1 1 1. But what I'll do is that I'll separate out their first bits first, and then I'll separate out the second bits first. So I'm going to write it as 1 by root 2 1 1 AB 0 0 AB, right? So essentially both are actually 1 0, but I'm writing it in this way, and I'm going to write it as 1 by root 2 1 1 AB. So these two ones 1 1 AB, right? So essentially it's 1 0 1 0 and this is 1 1 1 1. Okay, and the reason why I've written it in this form is that I can now take out this cat 1 1 AB outside, and I'm going to get 1 by root 2 0 0 AB 0 0 AB plus 1 by root 2 1 1 AB times 1 by root 2 0 0 AB plus 1 over root 2 1 1 AB. Okay, so it looks quite similar, like it now looks a bit more cleaner, because now you see that if the first 2 bits of these are 0 0, then the next 2 bits are 0 0. If the first 2 bits are 1, if the first bit of each of these Alice and Bob pair it's 1, then the next in the next share of qubits they are actually sharing an EPR pair. So this is how the state looks like. So this is cat phi 0. Similarly, you can check that cat phi 1 in the above representation is going to be 1 by root 2 0 0 AB 0 0 AB minus of 1 by root 2 1 1 AB times 1 over root 2 0 0 AB plus 1 over root 2 1 1 AB, right? So now the thing is that, okay, so this is how the share looks like, share of qubits looks like. Now suppose if we can perform an embezzlement, right, we'll show that how to actually win the game. Okay, so essentially they need to output a share of bits, a pair of bits A and B, such that A XOR B is K, and we'll see that if they can perform embezzlement, they can actually do this thing. So suppose if there is a share of, if there is a pair of operators which allows us to embezzle 0 0 to 1 by root 2 0 0 plus 1 by root 2 1 1, then what we can do is that we can apply that same set of unitaries controlled on their first qubit. So suppose UA UB psi is an embezzlement strategy. Then what we can do is that apply UA and UB controlled on first qubit being 0, right? So basically if the first qubit of these two pairs, if their first qubit is 0, then they'll apply UA. If Bob's first qubit is 0, then he is going to apply UB. And if it is 1, then they are not going to apply that operator. So suppose if these two are 0, then basically the next pair of qubits will be transformed to 1 by root 2 0 0 plus 1 by root 2 1 1 with fidelity greater than equal to 1 minus epsilon. So here what is going to happen is that my state cat phi k is going to be transformed to 1 by root 2 0 0 AB times, okay, so this is my original state, So here basically I can, in general, I can write cat phi k as, so this was cat phi 0, but I can write cat phi k provided I'm going to have a -1 to the power k sign over here. Okay, and if these two is 0, then the second pair of qubits is also will be transformed to APR pair. So the bit which I'll the state which I'll get after that transformation will look like as follows. It will be 1 by root 2 AB times 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB plus 1 over root 2 times -1 to the power k times ket 1 1 AB times 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB. So this I can express it as 1 by root 2 0 0 AB plus -1 to the power k times ket 1 1 AB times 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB. So this is how the transformed state is going to look like. Okay. So suppose if this is doable with fidelity greater than equal to 1 minus epsilon. Okay. So suppose the transformation is possible with fidelity greater than equal to 1 minus epsilon, which means that now I cannot distinguish, this transformed state from its original state with basically the probability being a trace distance between them, right? Because the probability of distinguishing between two states is given by half plus half of the trace distance, right? And if the fidelity is greater than equal to 1 minus epsilon, then the trace distance, so let's say this is fidelity between some rho and sigma, then trace distance between rho and sigma will be upper bounded by square root of 1 minus f square, which is going to be equal to 1 minus epsilon squared, which is going to be how much? This will be twice epsilon minus epsilon square. So this is less than equal to square root of twice epsilon, right? Epsilon is greater than equal to 0. And if the trace distance between two states is upper bounded by this value, that means that we cannot distinguish it with the probability at max half plus half of this order epsilon. So can't distinguish with probability. So if we have to distinguish them, we can only distinguish them with probability more than half plus half of order root epsilon, right? So half plus, so basically I can just get an order root epsilon sort of advantage over a random party who is trying to distinguish them. And now the thing is that suppose if they measure this state, so let's say that we have prepared this sort of a state ideally, then what they can do is that after performing that embezzlement, they measure their first sort of qubit in Hadamard basis, and that this is the state which we saw. This was the state which in order to distinguish between P0 and P1, we didn't require any entanglement, right? So this was the first game we saw, and we have seen that Alice and Bob can actually win that game with probability 1. So now they can still do that provided they have prepared it correctly, right? But if this is incorrect, right, then that means that you will be able to distinguish between your embezzled state and the incorrect state with probability more than half plus half order root epsilon, which will be incorrect. So basically at max the probability of failure on measuring Hadamard basis So measuring the first pair of qubits and returning A comma B is at max order root epsilon, right? And okay, so let me explain the reason more formally here. So the reason is that okay, so suppose if embezzlement is perfect, then measuring first pair of qubits to get A comma B gives us A XOR B equals K. So my first pair of qubits in Hadamard basis, right? That is in the plus minus basis, the eigenstates of X. So we have already seen that, right, in the last lecture how it happened. And okay, and since embezzlement succeeds with probability greater than equal to, okay, so since embezzlement succeeds to produce a state which is less than equal to order epsilon in trace distance from EPR, that will mean that we can't distinguish it from EPR with probability more than half plus order root epsilon. So this essentially means that the protocol must succeed with probability this implies that the protocol must succeed with probability greater than equal to 1 minus order root epsilon, right? Because if the success probability of this protocol is lesser than this, then it means that we are being able to distinguish between EPR pair and the embezzled state. So since it is not possible, so here basically the success probability of the protocol must be 1 minus order root epsilon, right? Okay, and now let's prove the converse. So firstly, what do we gain from this? So we have proved this claim that that embezzlement implies winning the quantum input game, but we know that embezzlement is possible with dimension of the order of 1 over epsilon sort of qubits. So here essentially it will mean that winning the game with probability 1 minus order root epsilon is possible with 1 over epsilon qubits, and winning the game with probability 1 minus epsilon is possible with 1 over epsilon square qubits. So this is a possibility result, right? And now we'll show that this exponential lower bound is also there. That lower bound is also exponential in 1 over epsilon in terms of dimension. So in order to show that, we'll look at the second claim. So the second claim, this says that if I can win the game, then it means high fidelity, right? So the other claim, which is that this implies fidelity embezzlement greater than equal to 1 minus order epsilon. So let's see how this turns out to be true. Okay. Suppose if there is some protocol which wins the game. So that protocol must start. Suppose there is protocol that wins this game. Okay, so let's say that it starts from the state cat phi k psi ab. So cat phi k is going to be my input state, and let's say my psi ab is my resource entanglement. Okay, so let's say we perform a transformation through unitaries VA and VB. Okay, so say VA tensor VB acting on cat phi k psi AB. So let's say it has transformed this state, and let's say that what I'm going to get is that let me actually separate out their first qubit each, right? And let's say it turns out to be of the form of alpha 0 0 0 0, and then the remaining state is S 0 0 AB plus alpha 0 1 0 1 AB, and then S 0 1 AB plus alpha 1 0 1 0 AB, and then I have S 1 0 AB plus alpha 1 1 1 1 AB, and then S 1 1 AB. Okay, so this is such that sum over ij alpha ij mod square must be equal to 1, right? And let us say that this is the first qubit they measure which produces their bit. So this is the assumption we are making, right? So ultimately when you output a bit, you are making some transformation, and in the end you are making a measurement, right? And you can always assume that this is a sort of a basis measurement by extending your state space appropriately. You can assume that this is always a standard basis measurement, and the operations are also unitary, right? So these assumptions we can make. So let's say that a measurement on first qubit produces A and B. Now for protocol to succeed, with probability greater than equal to 1 minus epsilon, we must have that alpha 0 0 square plus alpha 1 1 square is greater than equal to 1 minus epsilon, and alpha 0 1 square plus alpha 1 0 square is less than equal to epsilon. This is provided if k equals 0, right? And alpha 0 0 square plus alpha 1 1 square is less than equal to epsilon, and alpha 0 1 square plus alpha 1 0 square is greater than equal to 1 minus epsilon. This happens if k equals 1. Okay, so let's say that each applies a Z gate. Okay, so this is basically okay. So why is this true? Because ultimately what I want is that if k equals 0, then A XOR B must be 0 with probability greater than equal to 1 minus epsilon, right? So suppose if they measure their states, and you know that so essentially if you measure such a state, the probability of getting both zeros is going to be mod alpha 0 0 square. Probability of getting both ones is going to be mod alpha 1 1 square. And yeah, so basically these coefficients will the sum of squares of these coefficients must be greater than equal to 1 minus epsilon for them to succeed with probability 1 minus epsilon if k equals 0. And similarly, we have alpha 0 1 square plus alpha 1 0 square must be greater than equal to 1 minus epsilon for them to succeed with probability 1 minus epsilon if k is 1. Right, so this was for k equals 0, this is for k equals 1, and these are the remaining coefficients. So the remaining coefficients, they can, okay, so the remaining, so since we need to distribute a mass of 1, so I have to put in 1 minus epsilon here. The remaining epsilon I can put in alpha 0 1 square plus alpha 1 0 square over here. Okay, so now suppose each applies a Z gate on their first qubit. To produce the state ket mu AB, which equals ZA tensor I tensored with ZB tensor I times VA tensor VB on phi k on psi AB. So what is happening is that we are seeing that VA tensor VB produces this sort of a state. Okay, this state, and now if I apply, if each of them apply ZA and ZB, right, so they apply on their share of the first qubit. So they apply on the first qubit which they have, they apply ZA and ZB respectively, right. So this gives you the state ket mu AB. Okay, and now we can do that, we can take their inner product. Okay, so inner product between mu and VA tensor VB, this thing on phi k tensored psi AB. Okay, so I am seeing that, let's see that how much is the overlap between VA tensor VB and mu AB, right. So mu AB, if we see, so this essentially, let's see what mu AB is. So mu AB will have the 0 0 will remain as it is, 1 1 will also remain as it is, because here so here when ZA acts on 0 it doesn't do anything, when ZA acts on 1 it produces a minus sign, and then since there are two ones, the two minus signs get cancelled, but overall we will get a minus sign for 0 1 and 1 0. Okay, so here what am I going to get? I am going to get alpha 0 0 0 0 S 0 0 plus alpha 1 1 1 1 S 1 1, right, minus alpha 0 1 0 1 S 0 1 minus alpha 1 0 1 0 S 1 0. So this is what I am going to get, right. And so if I take the inner product with this thing, what I'm going to get is that I'm going to get alpha 0 0 squared, alpha 1 1 squared, and then minus of these two squares. So this is going to be alpha 0 0 square plus alpha 1 1 square minus alpha 0 1 square minus alpha 1 0 square, right. And so here let me see what it is going to be. So if k is 0, right, so here wherein the mass is distributed on 0 0 and 1 1, then we know that this part is greater than equal to 1 minus epsilon and this part is less than equal to epsilon, so therefore this is going to be greater than equal to 1 minus 2 epsilon. Whereas if k equals 1, okay, then what is going to happen is that this part is less than equal to epsilon and this part is greater than equal to 1 minus epsilon, so overall this sum will be at max of epsilon minus 1 minus epsilon, right? So that will be at max minus of 1 minus 2 epsilon. But what I can do is that with a sign, what I can do is that, so mu times minus 1 to the power k, if I put in over here, times VA tensor VB and phi k psi AB. So this is actually going to be greater than equal to 1 minus 2 epsilon for both the cases. So note that the mu which is produced is also dependent on k, right? So mu 0 and mu 1 are going to be different. So actually I should have written a mu k over here, right? And so what is going to happen now is that so phi k psi AB, if I apply VA tensor VB, and then mu k was nothing but so mu was produced by doing again VA tensor VB, and then we had ZA tensor ZB. So actually I can look at the equation in a slightly different manner. Now let me actually take VA tensor VB along with mu. So now what is going to happen is that VA dagger tensor VB dagger, okay, minus 1 to the power k, this thing acting on mu AB, this is going to be minus 1 to the power k phi k psi AB with fidelity greater than equal to 1 minus 2 epsilon. So overall, summarizing, what we get is that VA dagger tensor VB dagger times ZA tensor ZB times VA tensor VB on phi k psi AB, right? So here essentially what I'm doing is that so I have flipped this equation and I'm now looking at VA dagger tensor VB mu k, and now this is like the fidelity between phi k psi AB and VA dagger VB dagger applied to mu k. So and mu k is nothing but ZA tensor ZB VA tensor VB phi k psi AB. So this actually equals minus 1 to the power k phi k psi AB with fidelity greater than equal to 1 minus 2 epsilon, right? So here now essentially to summarize, what we did is that we can take phi k tensor psi AB, we apply VA tensor VB, we then apply ZA tensor ZB, and then we apply VA dagger tensor VB dagger. And what we do is that we either flip the sign of phi k tensor psi AB or we don't flip the sign, depending on whether k equals 0 or 1, right? So suppose if I would have done this sequence of operations on 1 by root 2 ket phi 0 plus 1 by root 2 ket phi 1, suppose we applied the sequence of ops on one by root 2 phi 0 plus 1 by root 2 phi 1 psi, what I'm going to get is 1 by root 2 phi 0 minus 1 by root 2 phi 1 on psi, right? And if you now see this 1 by root 2 phi 0 plus 1 by root 2 phi 1 is going to be nothing but 0 0, and this is going to be nothing but 1 by root 2 0 0 plus 1 by root 2 1 1. So essentially we will be able to embezzle our state, so using that same resource psi, and basically I can use the same set of operators, then I can do ZA tensor ZB, and then I can do reverse of those operations, and I'll be able to embezzle from the state ket 0 0, I'll be able to embezzle this EPR state, and this happens with fidelity greater than equal to 1 minus twice epsilon, right? Or 1 minus order epsilon. So basically, if the original state I can do with fidelity, like kind of if I can win the game with probability with probability 1 minus epsilon, I can perform an embezzlement with fidelity 1 minus 2 epsilon. So here essentially the thing is that in order notation, if the probability of failure is order epsilon, then the probability of failure of entanglement in terms of fidelity is also order epsilon, right? So essentially, if I want to win the game, if you want to win with or basically if you want to win with probability greater than equal to 1 minus epsilon, which means that performing embezzlement with fidelity greater than equal to 1 minus 2 epsilon. So this requires D, which is at least exponential of order 1 over root epsilon, right? So this is what we had shown earlier, and now we can combine these two results. So basically, even if you win with probability 1 minus epsilon, you basically are working in an entangled space with dimension exponential of order 1 over root epsilon, right? So this is not the number of qubits, this is the dimension of the space. The number of qubits is 1 over order 1 over root epsilon. Okay. So basically what we have shown is that there is a game, right? And as I bring epsilon closer and closer to 0, that is, I want to bring the success probability closer and closer to 1, then essentially I'll need more and more number of qubits or more and more dimension of the Hilbert space. But the thing is that I can, so here it appears that that the question is that whether a probability of 1 is possible, right? So yeah, so that is actually a suspense question, but the answer is indeed yes, that if you indeed have infinite dimensional systems, you can win with probability 1. Proof of that is slightly different. It will require us to go into C-star algebras. So we'll try to see if we can cover that in the next few lectures. Yeah, so that's it for today. So, but the cool thing is that that no finite dimensional game can win the probability with can win the game with probability 1, but you can get closer and closer to that with finite dimensional systems. Okay, so thanks, bye.